Yet even as scientists celebrated this breakthrough, another team working halfway around the world was about to reveal that the story of cosmic water delivery was far more complex than anyone had imagined. Japan's cosmic detective work. In the precision-engineered halls of the Japan Aerospace Exploration Agency near Tokyo, another team of scientists examines their own cache of cosmic treasure. The fluorescent lights hum quietly overhead as researchers in pristine white laboratory coats lean over electron microscopes and mass spectrometers, analyzing samples that traveled an even more circuitous route through space. The Hayabusa 2 spacecraft returned to Earth in December 2020 carrying fragments of asteroid Ryugu, a diamond-shaped pile of rubble orbiting between Earth and Mars. These samples would reveal secrets that complement and complicate the story emerging from Bennu's fragments. Dr. Shogo Tachibana adjusts the focus on his scanning electron microscope as images of Ryugu's interior structure appear on his monitor. The samples reveal a fundamentally different type of water storage system than what American scientists discovered in Bennu's clay-rich matrix. Ryugu's water exists primarily within magnetite crystals and carbonate minerals that form through entirely different chemical processes. Where Bennu's water became trapped in phyllosilicate clay structures through gradual aqueous alteration, Ryugu's parent body experienced rapid heating events that drove water into different mineral phases. The isotopic analysis presents an intriguing puzzle. Ryugu's deuterium to hydrogen ratio differs measurably from Bennu's signature, suggesting these asteroids formed in separate regions of the early solar nebula or experienced different thermal histories. The Japanese team measures deuterium levels approximately 30 parts per million higher than the Arizona samples, a small but significant difference that points to distinct origins for these water-bearing bodies. This isotopic variance indicates that Earth received water from multiple asteroid families rather than a single population of similar objects. Advanced electron microscopy reveals microscopic structures invisible to conventional analysis techniques. Within Ryugu's carbon-rich matrix, water molecules nestle inside cavities barely nanometers across, trapped when organic compounds solidified billions of years ago. These molecular pockets preserve water in its original state from the solar system's formation period, offering scientists pristine samples of primordial H2O. The water content reaches concentrations of 8,000 parts per million in the most hydrated samples, lower than Bennu's measurements, but still representing substantial quantities for such an ancient object. The chemical composition of Ryugu's samples tells a story of violent early history followed by gentle preservation. Carbonate minerals within the asteroid fragments show evidence of fluid activity that occurred within the first few million years after the solar system formed. This aqueous alteration happened much earlier than similar processes recorded in meteorites that fell to Earth naturally, suggesting that Ryugu's parent body experienced rapid heating and cooling cycles during the chaotic period when planets were still assembling. Comparison between the Japanese and American asteroid samples creates a detailed map of water distribution in the primordial solar system. The two asteroids formed at different distances from the Sun and experienced different degrees of thermal processing, yet both retained substantial water inventories throughout their 4.6 billion year journey through space. Spectroscopic analysis shows that Ryugu contains a higher proportion of organic compounds mixed with its hydrated minerals, including complex carbon molecules that serve as precursors to biological chemistry. The Micro-Omega imaging spectrometer identified signatures of hydrated phases throughout Ryugu's sample collection, confirming that water played a fundamental role in the asteroid's formation and subsequent evolution. The distribution pattern shows that water-bearing minerals concentrate in specific regions of the asteroid fragments, suggesting that fluid flow within the parent body followed predictable pathways based on temperature gradients in mineral composition. These hydrated zones preserve chemical signatures of the original aqueous environment where water dissolved and redistributed various elements. Laboratory analysis reveals that Ryugu's subsurface material contains more water than its surface layers, indicating that space weathering processes gradually dehydrated the asteroid's exterior over billions of years. Solar wind bombardment and micrometeorite impacts slowly stripped water molecules from exposed mineral surfaces, while the interior remained protected. This discovery explains why ground-based telescopic observations often underestimate the water content of similar asteroids by analyzing only their weathered outer layers. The organic compounds mixed with Ryugu's water-bearing minerals include amino acids, nucleotide bases, and complex hydrocarbon chains that represent the chemical building blocks of life. These molecules form through reactions between water and carbon-rich materials within the asteroid's parent body, demonstrating that the same processes that delivered water to Earth also synthesized the organic compounds necessary for biology. The intimate association between water and organic chemistry in these samples supports theories that asteroids delivered complete chemical packages to early planetary surfaces. Combined data from both missions reveals that Earth's water supply originated from at least 2 distinct asteroid populations with different formation histories and chemical compositions. The American samples show evidence of prolonged aqueous alteration in a relatively cool environment, while the Japanese samples record rapid heating and cooling cycles that drove water into different mineral phases. This diversity explains the complex isotopic signature of Earth's oceans, which contains a mixture of water sources rather than a single uniform composition. Statistical analysis of the combined sample data suggests that water delivery to Earth occurred over millions of years rather than during a single catastrophic event. The different asteroid populations arrived at different times as their orbits evolved under planetary gravitational influences. Early bombardment phases delivered water-rich materials like those found in Ryugu, while later impacts brought the clay-bearing asteroids similar to Bennu. This prolonged delivery process allowed Earth to accumulate water from multiple sources while maintaining liquid oceans at its surface. The chemical complexity revealed in these asteroid samples explains why Earth's oceans contain such a diverse array of dissolved minerals and trace elements. Each asteroid family contributed its own chemical inventory to the growing oceanic reservoir, creating the complex solution that supports modern marine ecosystems. The sodium, chlorine, magnesium, and sulfur found in seawater can be traced back to specific types of asteroid-delivered materials based on their isotopic signatures and mineral associations. Modern analytical techniques allow scientists to reconstruct the entire sequence of water delivery events that shaped Earth's hydrosphere. The Japanese and American samples provide complementary pieces of this cosmic puzzle, each revealing different aspects of how water moved through the early solar system and accumulated on planetary surfaces. Yet, as researchers celebrated these groundbreaking discoveries about asteroid water delivery, instruments scanning the skies were about to detect something that would challenge their understanding of where cosmic water could survive: the moon's hidden ocean.